Okay, so we just discussed a second ago that, I mean, just strategically speaking, either way you try to solve for either variable here, the bounds on the ensuing integral are going to be ridiculous at best. And so surely there's an easier way. The easier way that's been discussed in this section is symmetry, so I think it's bound to be symmetry. Okay, so let's think about how this might be symmetric. Now, looking at the function, I notice that there's some potentially very useful minus signs there and there, right? And so in particular, if I replace y with negative y, I see how those are going to kind of, something interesting is going to happen if I replace y with negative y. Right? By the way, if I replace x with negative x, nothing happens because x squared doesn't change when you replace x with negative x. And ditto, that x squared doesn't change. So the function's got even symmetry if you change the sign of x. Okay, so let's consider the possibility, fingers crossed, that maybe this has odd symmetry the other way. So let me recopy here. Well, I want to replace y with minus y, and I have to draw a picture. If you take a point, x comma y, and you say, well, where is x comma minus y? Down here. Right, so this reflection, yeah, it's actually a reflection over the x-axis. Right, so Rx of xy is x comma negative y. Yeah, everybody good? All right, so now does the function have the required odd symmetry? Well, let's see here. The function is, yeah, okay. X squared y squared e to the y minus x squared y squared e to the minus y. And let's see, okay, all right, fine. So what is f of x? Well, what is f of the reflection? Which is f of x comma minus y, and that is, being very careful, x squared minus y squared e to the minus y minus x squared minus y squared e to the minus y. Now, let's take a pause on that. Does everybody see how I plug that in? Because I have to plug in minus y everywhere I see y in the above formula. It's really easy to lose some minus signs in that process. Okay. Well, good news. That's x squared y squared e to the minus y minus x squared y squared e to the y, which conveniently is exactly the negative of f of the original point. Okay, so, and therefore, f is odd over the x-axis. Okay. Yeah. Okay. Right. Okay. What about our domain? Well, gosh, the domain's tough, but the way we can see this is that this equation doesn't change when you replace y with minus y.
Yeah.
Right? And so, in other words, if we were to reflect this curve over the x-axis, we would do that by replacing y with minus y, and clearly nothing happens there. So we can just, you can just argue that kind of in words, right? That flipping this curve over the x-axis by replacing y with minus y, the equation is unchanged. Therefore, the boundary curve is symmetric. Therefore, the domain is symmetric. Integral equals 0 by symmetry. So yeah, not that bad.
And so the domain doesn't change.
Yeah, that's so. A domain is symmetric over a given line if, when you reflect over the line, the domain does not change. Everybody happy?